After discussing the concepts of force, energy and power, we will now consider the energy conversion that takes place in solar cells. Photovoltaics involves the direct conversion of light into electricity. In the next video, we will learn how this conversion takes place. In this video, we will focus on some important properties of light and on solar radiation. We will learn about the basic properties of light. We will discuss the spectrum of electromagnetic radiation and the radiation spectrum of our Sun. Then we consider the irradiation on the surface of the Earth, and finally we will discuss the standard test conditions. As we will discuss later in this course, light is a form of an electromagnetic radiation. The properties of this radiation can in some respects best be described by a wave. Such a wave is shown here, propagating at the speed of light. The distance between the two wave peaks is known as the wavelength, indicated by lambda. Over a distance of one wavelength, the wave undergoes exactly one cycle. The number of cycles that occur in 1 second is known as the frequency, indicated by nu. The frequency expressed in hertz is equal to the speed of light divided by the wavelength. In other respects, light is best described by a flow of light particles. Such a particle is called a photon. The energy of a single photon can be calculated by multiplying the photon frequency by Planck's constant. Both the wave and particle properties of light will be more extensively discussed in the section on optics. The wavelength and the frequency of light are defining properties that dictate how electromagnetic radiation interacts with matter. Let's look at the spectrum of electromagnetic radiation to get a better understanding of these properties. This blue bar is the full spectrum. We introduce an axis for the wavelength. The axis ranges from wavelength smaller than 10 to the power minus 16 meters to over 10 to the power 8 meters. We also introduce an axis for the frequency, for which we use the speed of light in vacuum. The frequency axis ranges from 1 Hz to about 10 to the power 24 Hz. Since both wave properties are inversely related, the error of increasing wavelength size and frequency are pointed in opposite directions. The part of the electromagnetic spectrum that us humans can observe with the naked eye is very small in this scale. It's indicated by this colorful line. If we take a closer look, we can see that the visible spectrum ranges from blue and violet light to red light. We introduce a new axis for this part of the spectrum with a scale in nanometers. We can see that the visible part of the spectrum ranges from roughly 400 nanometers to about 700 nanometers. All electromagnetic radiation outside this visible spectrum is invisible to our eyes. If we look at the radiation with a wavelength smaller than that of visible light, we first encounter ultraviolet light, followed by X-rays with a wavelength ranging from 0.1 to about 10 nanometers. X-rays are also known as Röntgen radiation and are used to look inside objects, for instance in medical imaging. Photons with even smaller wavelengths are known as gamma rays. If the wavelength is about 100,000 times smaller than a nanometer, the photons are called cosmic rays. If we look at electromagnetic radiation with a wavelength larger than that of the visible light, we enter the infrared part of the spectrum. Infrared light has a wavelength up to about a millimeter. Photons with larger wavelengths are considered microwaves. This is a type of radiation we use to heat food in a microwave oven. The large wavelength part of the microwave spectrum is used for GPS technology. In addition, the current third generation mobile networks, abbreviated with 3G, operates in the 1.6 to 2.1 GHz range. While the 4G is working in the 2 to 8 GHz range, the 10 to 90 GHz range is being explored for the 5G technology. Electromagnetic waves with a wavelength between 1 meter and 1 kilometer are in the radio wave part of the spectrum. FM radio waves are in the small wavelength part of the radio wave spectrum, while AM waves have a large wavelength. Even larger wavelength photons ranging from 1 kilometer to over 1 million kilometers are considered long radio waves. In photovoltaics, we are mainly interested in ultraviolet, visible and infrared light, as we will see in a moment. First, we will discuss some radiometric properties of incident light, namely irradiance and irradiation. The irradiance is defined as the total power density incident on a surface from a radiant source. The irradiation is the total energy density incident on a surface. Since the power can be defined as energy per unit time, the irradiation can be obtained by integrating the irradiation over a certain time interval. The power emitted by the sun amounts to about 380 times 10 to the power 21 kilowatts, which amounts to about 3.2 times 10 to the power 27 kilowatt hours per year. The sun emits light more or less equally in all outgoing directions. Earth therefore only receives a tiny fraction of the power radiated by the sun. This tiny fraction sums to about 6 times 10 to the power 13 kilowatts. To put that into perspective, this equates to roughly 10,000 kilowatts per person on planet Earth. Our global average power consumption is about 2.3 kilowatts per person. The fact that the power received by the sun can supply this number many times over is a testament to the potential of photovoltaic energy. Not only the total power incident on the surface is important, also the spectral distribution of the incident power plays a major role. Not all wavelengths of light are emitted equally by our sun. Moreover, solar cells can only use a fraction of the incident wavelengths. We will therefore discuss the spectral emission characteristics of our sun and the spectral characteristic of the solar irradiation on Earth in the next video.